G'day everyone, this is Mackie Lee, your Quantum Odyssey tour guide, and today we will do a short review. But please bear in mind, all of the first ring videos will be re-recorded due to quality concerns after I have rewatched these. So especially the day 4, day 5, day 6 ones after I realized that my audio input is too loud and it's starting to break. They will be re-recorded and they will be restructured. Today we will do on a short review on all of the first ring qubit gates that we have gone through. We will also give you like a short linear algebra description of each of these gates before we formally dive into linear algebra after finishing the Quantum Odyssey. And we will also discuss about what will be in store for you after. So Quantum Odyssey, we have this map. And so far, what we have learned is this. So we have this 1, 2, 3. The first three are pure tutorials. So these are here to teach you about the very basic mechanics of this game. And on the third one, you have already seen that there are the Z gate and the S gate for you as well. The first quantum gate you will study specifically is the X gate. We have the Z gate as well. So as you complete the topics, we have let's draw this a little better. So X gate, Z gate, the control gate, which technically isn't really a gate at all, the H gate, the S gate, and the Y gate. And each of these electrons, let's say nodes or something, are connected. They are reviewed in order, so the first ring contains 9 elements, 9 electrons. And there's also like these branching paths as well, which leads to these individual challenge puzzles, which usually go between the rings as well. And each of them are like a follow-up to the preceding main electron, which is on the ring. And these usually do not lead to any further exercises. While other paths lead to more exercises. For example, you already have like a branching path after completing the third electron, which leads you to a path of red rings over there. So on. And there is a ring that leads you to understanding the S gate and eventually the T gate, and then identifying the quantum algorithms like Grover's search and the quantum Fourier transform. So we have phase, we have SX, then T gate. The map that I have drawn there actually came mostly from a live stream dedicated player has done. He has dedicated spent like an entire night just to grind on this game, and he has been progressing really fast. He's now number 1 in Quantum Odyssey. So I have been learning from him, from that guy from, I don't know like what's his gender or something, but just say like them, like that. And then there's another one that leads to the classic algorithms like AND. So it's going to be AND, then XOR, then OR, then NAND, so on. So these gates can be implemented as well. So this is the overview of what will be in store for you. So again, there will be like multiple paths throughout each of these, and I'm going to give you like a short overview on how to solve these. I'm going to explain them for at most 10 minutes before we do on like more of the hands-on stuff as well. The hands-on definitely will take a bit more time as long as I'm able to like dedicate the time. So if it's a little bit like too long, then just let me know, because in this age like people are like more interested in like these short videos and stuff. But once again, here is a summary of what we will do. One of the paths will be about classical computation using quantum gates. Classical gates using quantum gates. This includes the AND, the XOR, and the inclusive OR, which is just nothing more than an and XOR XOR over there. We also have the NAND and the NOR gate, which are universal for classical computation. So you can express any of the common gates and or XOR using and not using only NAND and NOR. And finally, we have the half and full adders. The other half we will discuss about is the quantum algorithms. So the most famous quantum algorithm is the Shor's algorithm and the Grover's algorithm, especially Shor's because it provides exponential speed up. But the Shor's is ultimately just a special case of quantum Fourier transform. So quantum Fourier transform, quantum Fourier transform, and the other one would be Grover search. Grover search. And there's another important phenomena called phase kickback. It took like in the 1990s to develop these useful quantum algorithms. It's a double whammy to devise these stuff, because not only do you have to implement the algorithm in quantum terms, but it also have to be better than the best known classical ones. And finally, the first branch, which are the red ones, are the challenge path. So ultimately, the path of Quantum Odyssey, the rings, are actually more or less like a tree structure. With many leaves, there are long paths, and then there are these inter-ring exercises which are almost always dead ends. We will, once again, I'm not going to tell you in advance how we will fold up. in the spirit of Quantum Odyssey, but we will definitely aim to complete Quantum Odyssey in 50 days. Okay, so let's explore what we have reviewed on the gates. So we have, again, let's start with the X gate. The X gate, the Z gate, the control gate, the H gate, the S gate, and of course the Y gate. The other gates you will see are the T gate, the SX gate. So these are like partners in crime. You will also see the RT gate. So these are here to like provide an unequal superposition. And it looks very much like the ordinary H gate, except the cross terms are thinner. So that's the RT gate. So it's an unequal split. We have the RX gate, which splits any blue single sigil into a blue and a yellow. So that means the two halves, one of them have the same phase and the other one is rotated 90 degrees clockwise. So these are like the things you will see. Regarding the inter-ring challenges, the first one, the one that's based on the X, contains only X's. So this is going to be like exercise. The other path from like electron number 4, and the Z one, the Z exercise would contain an Z and an X, and so on. Eventually, the Y branch would contain all of the previous 5 as well. So, according to the map that we have for descent mode, over there. So here, this thing would contain only X, that will contain X and Z. The control gate would likely contain control X and Z. The Hadamard would contain these. The other path that comes from Y would probably come from like Y and all others over there. So, and these provides hands-on follow-up to the main electrons. This is your review. Our next topic is to express about the matrix representation of these gates. So matrices are nothing more than rectangular arrays of numbers. But the main interest of matrices is about matrix multiplication. This is mathematics. The complex number, the phase change, You can express them like literally without using mathematics, like how much it is turned, but the rectangular representation still is mathematics. The polar representation is there to visualize what happens if you rotate a complex number about the complex plane, which is realized using the Z, S, and T gates. Okay, so we have this. So the X gate has expressed as a matrix would be this. That the right member, the left member comes from the right member, the right member comes from the left member. So from, so let's try to make a mnemonic over there. From, left, right, left, right. So left wire, right wire, between two wires which differ by 1 qubit. Z puts the sigils in place, but the right sigil, the sigil on the right lane, gets sign flipped. That means it's rotated 180 degrees about the complex plane. The control gate basically splits the thing into the elements in two halves, like divides it in two halves, and then applies only on the right half. So it's going to be I, and it's going to be U. The Hadamard gate is obviously the harder one to explain, but here is what happens. The Hadamard gate means the sigil on the left would be split to two half-size sigils of radius 1 over root 2 to both sides. The right would be the same, except that the one that stays on the right gets negated to its negative. There is also an algebraic way to simplify this. It's going to be 1 over root 2, 1, 1, 1, then minus 1. So these are 2 by 2 matrices, thinking 2 by 2 matrices. You might have saw like these matrices in game theory, 2 by 2 Eisenhower matrix, in statistics, like literally like positive or negative predictive value. Like these are all applications of a 2 by 2 matrix. The S gate would be 1 on the left half, the sigils stay in place, and the right half it would advance by a quarter turn, which in polar form it will be 1, and then e to the I half pi. Y, on the other hand, is like you switching and then applying an S, and then forming a global phase shift all at once. But the most important thing that makes a Y gate is that it both switches the position and the signs. In this case, the sigil on the left would be transported to the right and would gain its step. So it's going to be I over there. That means the right qubit on the output comes from the left qubit, left lane, and vice versa, except this time it's negative I. That means the right sigil would be put to the left, so now it's on the top row, or the left sigil on the output, that means the top row, comes from the right. Likewise, we will also express the mathematics behind the remaining 4 gates, which this is called the T gate, this is called the SX gate, this is called the RT pi third, and RX pi quartered. You will see these as well. The T gate is like the S gate and the Z gate, like a phase gate, except this time it does half of what S does. This time we now have this 1, then we have I, 1 plus I over root 2, like a 90-degree right isosceles triangle of unit radius would become this. In polar form, it's going to be 1, and then e to the I pi quartered. The SX gate will be transform it into this. The ones on the main diagonal, that means those which stay in place, would all advance up by an eighth of a turn, and those which cross are advanced backwards. And all of them would be divided by 1 over root 2 to maintain a property we'll later call it unitarity. In this case, theta, in this case, let's call this. This up arrow will be 1 plus I halved, and then the right other arrow would be 1 minus I halved. We notice that up ascending arrows is equal to descending arrow, its square norm, and it is identically equal to 1 plus 1 halved. It is equal to quartered. It is equal to 1 halves. RT pi third is slightly trickier, but let's explain this to you. So 1 now becomes 1 over root 2 over 3, then root 1 over root 3. So if you want to get the numerical value of that, so 2 over root 3, 1 over root 3, this one would be 1 over root 3, then minus 2 over root 3. So it's like the Hadamard gate, except it divides the things unequally. So square root of 2 over 3 would be, in this case, 0.8182 Likewise, square root of 1 over 3 would be 0.57. It is like it is like splitting the cubit in the 60-degree angle. So and the last one we will discuss about the Rx pi over 4 behaves just like an H-gate, except this time the cross paths are all of negative I. So these are this introduction, an impression on the matrix representations. Likewise, we will then generalize this to another important topic called adjoints and unitaries. So adjoints. And unitaries. So when you examine the S-gate, you realize that the S-gate is not its own inverse. The S-gate inverse instead is the S-dagger gate called, which the right half would be just the conjugate of the S-gate. While on the other hand, the X-gate is its own inverse. The Z-gate is its own inverse. The H-gate is its own inverse. And then likewise, the Y-gate is also its own inverse. Notice that the crisscross, green, yellow, yellow, green. So we have this X, Z. So X dagger is equal to X, Z dagger is equal to Z, H dagger is equal to H, and then Y dagger is equal to Y. This is this. S dagger is not equal to S anymore. But we also note that S dagger squared is still equal to Z. Anyways, like S dagger is like the other square root of Z. So mathematically, the adjoint of the adjoint is mathematically the conjugate transpose. Conjugate transpose. But then there's another thing. The unitary means the adjoint is equal to its inverse. And we will explain to you after Quantum Odyssey why this unitary is so important. Or somewhere like in the middle of the 50-day challenge, why unitary is such a core concept in quantum computing. So adjoints and unitaries. Likewise, we will explain to you the rotation gates. The rotation gates are the next set of gates that you will learn to identify. These are the first one and the most basic one is the RZ gate, which leaves the left half untouched but the right half rotated. So this is RZ. So RZ of theta is equal to this. E to the we have actually two forms, but let's do the slightly more Z-like form. It's 1, then we have e to the I theta. E to the I theta. So we can say that the Z gate is RZ of pi. The S gate is RZ of half pi. The T gate is RZ of quarter pi. Let's examine the Y gate. The Y gate would be this thing. The Y gate, RY gate, and this is actually the most familiar of the gates you will see in many advanced quantum circuits. So RY of theta is nothing more than your familiar rotation gate of the rotation is just by half. So cosine theta over halved minus sine theta over halved. Sine theta over halved, cosine theta over halved. Likewise, we have the Rx gate. The Rx gate also behaves like a Hadamard as well, except this time the Hadamard looks more symmetric and it can be seen as a hyperbolic rotation. So it's going to be cosine theta halved, cosine theta halved on the diagonal. And then on the antidiagonal it is just going to be minus I sine theta halved, minus I sine theta halved. You will see like these gates later on, but nevertheless you might need to use the Ry of pi third. So that means RT of pi third, which is based on the Ry, to solve certain problems which involves splitting sigils into 3. And then an Rx is mostly there for like just a shortcut to transform a qubit of the z eigenstate into a y eigenstate. So that means two qubits whose directions are 90 degrees apart. So once again, thank you for waiting so long and for staying. So thank you. Very much, and remember that tomorrow will be Good Friday. But please remember, all of these sessions will be re-recorded to make it like more better for rewatching, because it will be like harder to like look up to like see like should you use like my videos as a reference or like as a hands-on session, because so far after looking at the analytics it doesn't look too good, although I have been gaining some subscribers. But once again, I'm going to re-record all of them around this Easter, while trying my best to make a shorter video on each of the topics of the remaining rings. For example, I will provide a solution to one of the more challenging problems on one of those exercise rings, and provide you some insights, much like how the creator of Quantum Odyssey has been making some himself. So, but please bear in mind, I'm going to re-record them, and I know like it may require some editing, but the re-recorded version will definitely be of a better quality than that. Thank you. Hope to subscribe and like my channel, and good luck. Have a good Friday.